It is my great pleasure to introduce our second speaker today, Mark van Hoeij. So Mark is a professor of mathematics at Florida State University in Tallahassee, USA. He is a world expert in computational mathematics and computer algebra, that is in the art of designing efficient algorithms for manipulating mathematical objects in an exact way. For instance, among many other contributions, Mark is well known for his algorithms for factoring polynomials with the rational coefficients, for computing parametrizations of algebraic curves, and for factoring linear differential operators. These algorithms are the fastest ones for each of these tasks, both in theory, but also in practice. Mark's algorithms, actually mostly implemented in the computer algebra system Maple, are used in the daily lives of researchers in number theory, combinatorics, and mathematical physics. But today, Mark will speak about something else, about zometool construction toy, and of course, about the fascinating mathematics underlying it. So please, Mark, the floor is yours.
Oh, thank you very much. So today's talk is about zometool. Just to show you a couple of things, like things that you can make with zometool. So it's basically a construction toy, but there's some interesting math behind it, and that will be the topic of today. So first, the golden ratio is probably the most beautiful non-rational number. It's 1 plus square root of 5 over 2. So and let's denote that with tau. And then z denotes the set of integers, whole numbers. And then z tau is the set of numbers that you can write as an integer plus an integer times tau. And let's call these the golden integers, because they're made from the golden ratio. Now, the problem for the problem session is the following. So let's say you start at the point 0, and in each move you can move either left or right, and the distance you can move is either 1 or tau. So after, let's say, n plus n moves, you can reach, for example, this golden integer. And now your goal is you want to get back as close as possible to 0, but without actually being at 0. So you want the gap between where you land and 0, you want that gap to be as small as possible. Well, after one move, you can only be, because you can, remember, you can only do this. After one move, you can only reach these points. So then the one that's closest to 0 is 1. And after 2 moves, you can reach these, but you want to get close to 0 without being at 0. So the smallest gap from 0 is this, which happens to be the same as tau inverse. And after 3 moves, the furthest you can get from 0 is 3 tau, but the closest you can get to 0 is 2 minus tau. You see, you make 2 moves to the right of size 1, and then 1 move to the left of size tau, and then you reach this point, and that's the closest you can get to 0 after 3 moves. So, so notice here, in all of these 3 cases, the closest one was a power of tau, tau to the 0, tau to the -1, tau to the -2. So let's look at powers of tau. First, I'll look at positive tau, powers of tau, and then negative powers of tau. So if I take positive powers of tau, tau to the 0, tau to the 1, tau to the 2, you see, so tau square is equal to this, and then using this relation, every time you see a tau square or a higher power of tau, you can rewrite that using to lower powers of tau. Okay, and then if you write the powers of tau in this format, then they look like this. But now notice there's something funny about these coefficients, right? So these numbers 1, 1, 2, 3, 5 are Fibonacci numbers, and the numbers in front of the tau are also Fibonacci numbers 1, 1, 2, 3, 5, 8. So why is that the case? So why is a power of tau, if I write it in this way, why do I always get 2 consecutive Fibonacci numbers? Well, the reason is because tau to the power n plus 2 is the sum of the two previous tau powers, and the n plus second Fibonacci numbers is also the sum of the two previous ones. So they satisfy the same recurrence relation. That's why this happens. Okay. So now let's look at negative powers of tau. Tau to the -1 is this, this. And now I once again get Fibonacci numbers, except with plus or minus sign. So here I have Fibonacci numbers, and here I have Fibonacci numbers. So so negative powers of tau are also golden integers, but this time you get plus or minus Fibonacci numbers. So now this will be the problem for the problem session. So let's say we take 3 consecutive Fibonacci numbers, but the next one is always the sum of the previous 2. So if I have 3 consecutive Fibonacci numbers, then the biggest one is the sum of the previous 2. So for example, these 3 numbers could be, for example, this. So now the goal for the problem session is to prove the following. So let's say you make at most this many moves. Each is of size plus or minus 1, or of size plus or minus tau. Then the closest you can get to 0 without being at 0 with this many moves is you make, for example, this many moves to the right of step 1, and then you make this many moves to the left of step tau. That's the closest you can get to 0 without being at 0. And then in that case, this here will actually be equal to that. So in general, if m and n are arbitrary numbers, then this number times this number, the square root of 5 disappears. So this product is an integer, and a non-zero integer has absolute value at least 1. So if m and n are arbitrary, then this is then this here is some positive integer divided by that. So in the smallest possible case, this here is 1 divided by that. Now this is equal to that, and this 0.6 is less or equal than 1. So this is greater or equal than that, which is that. So what I'm saying is, if we take m and m to be these Fibonacci numbers, then we can make the gap this small, and that's greater or equal than that. And now what you now have to show is that this is optimal. So with this many moves, you cannot get closer to the origin than this number. And in particular, after at most n moves, the gap is either 0, you're exactly at 0, or the distance, the gap from 0 is at least this. Okay, so that's the problem session gap problem. And now the zone gap problem is the following. If you take, say, n zone pieces, like here I have 3 zone pieces, and you put them together, and now you're wondering, so let's open this up. You're trying to put this together, and you're wondering, is this just a pretty good fit, or is this an exact fit? So how would we know? Well, the zometool gap theorem is pretty similar to the gap problem for the problem session, except that it's in 3 dimensions instead of 1. But the proof is very similar, basically. So and this theorem says that the gap is either 0 or it's pretty big, at least this. So 0.7 divided by 3. That's still a pretty that's still a pretty big gap. So basically, the gap theorem says a gap is either so large that it's obviously non-zero, which isn't the case here, or it's a mathematically exact fit. So from now on, if it looks like it's a pretty good fit, that means it's actually mathematically exact. Okay, and that also means that with the gap theorem, I can actually prove things just using the zometool constructions. Because if it looks like a pretty close fit, then it's a mathematically exact equality. Okay, so now we have already seen a theorem about zometool, but now the question is, well, what exactly is a zometool? And now, yeah, for the mathematicians among you, I can give a really short answer, and it's just this right here. But of course, this short answer will require some explanations for the rest of us, So if I told this, for example, to Harm Derksen, if I told him just this, that would be enough information. But for the rest of us, I'll explain this answer. So the short answer is A5 is the group of rotational symmetries of the icosahedron. Now, what is an icosahedron? Well, that's this thing right here. And what are the group of rotational symmetries? Well, those are rotations that send this thing back to where it was. So, for example, if I take this thing and I make it 1/5 of a turn, then it looks exactly like it was before. But I can also, if you look through it this way, if I now, from this direction, if I take this axis of rotation, okay, and if I then rotate it 1/3 of a turn, it looks exactly like it was before. So all these rotations combined form what's called a group, and that group is called A5. And that group basically determines everything there is to know about zometool. But before I can really explain that, let's show some simpler examples of symmetry groups. So let's look at this square. Now, what are all the rotations that send the square to the square? Well, you can rotate it 0 degrees, or 90 degrees, or 180 degrees, or 270 degrees. Any one of these rotations will send this picture to itself. But they do move. But if I put names on the vertices, then those names do move. So, for example, if I rotate with 90 degrees, then A goes to B, B goes to C, C goes to D, and D goes to A, right? And if I do that 4 times, then everything gets back where it started. Okay, so we'll say that a rotation of 90 degrees has order 4, and order 4 means how often do you have to do something to accomplish nothing. Okay, so if I rotate this thing 90 degrees 4 times, then I've accomplished nothing. Everything is back where it was. So now this rectangle has a different group of rotations, because if I rotate this one 90 degrees, then it will look different. So the rotational symmetries of the rectangle, there's just 2 of them. Either don't rotate nothing or rotate 180 degrees. Okay, and the rotation of 180 degrees, that has order 2, because I have to do it twice to accomplish nothing. Okay, so next, so what is a group? Well, a group is a collection of operations, and in such a way that every operation in your group has an inverse. For example, the inverse of this is this, because rotating 90 degrees one way has the same effect as rotating 270 degrees the other way. So every element has an inverse, and every time if you have 2 elements and you compose them, it's again an element of your group. So for example, if you compose this with itself, you get this, and that's again an element of the group. And if you rotate this with itself, then you get a full turn, which is the identity, because it puts everything back in its place. Okay, so this composed with itself is also an element of the group. It's this element, and that element is called the identity. Now, in the previous slide, I went from a square, then I took a square and I looked at all the rotations that send the square to the square, and then I got a group. But if I now forget the square, and if I only have this group, then I can recover the square. So imagine just erase this square right here and just pick some vertex, let's say A. Now, if you apply all these rotations to A, then you get all these vertices back. This one, this one, this one, and this one. So if you have a square, you get a group. But if you have the group of a square, you can also get the square back. Just pick a point, apply all the rotations, you get the vertices of a square. And the same is true for the icosahedron. Let's just figure out all the rotations of this thing, and now throw away all the vertices except this one. Now apply all the rotations, and then you get all the other vertices. So you get the object back. So the point is that a group, so like a square like this, or its group of symmetries, you can go from one to the other. Okay. Now let's look at what are the rotational symmetries of a cube. So there's one rotation of order 1, namely if you rotate it 0 degrees, then everything stays put. Now there are 9 rotations of order 2, because, for example, I can take this rotational axis, you see it right here, stick it straight to the middle, and then I can rotate it along this axis by 180 degrees, and that has order 2. And there are 3 of these, but there are 6 of another kind of rotation. If I put the rotational axis of symmetry like along the side here, so basically in this direction, so if the rotational axis goes through this point and this point, then I also have a rotation of order 2, right? And a rotation of 180 degrees that sends the square back to the square. So there's 9 of these. There's 8 rotations of order 3. So for example, if you line up this point with this point, and now if you rotate it 1/3 of a turn, then everything is back to where it started. And then there are 6 rotations of order 4. These are kind of obvious. I can rotate this 90 degrees this way, and I'm back to where I started. Or I can rotate it 90 degrees this way, and I can do this for this axis, and for this axis, and for this axis. So these are all the rotations of a cube. Now there's a simple way to count all of them. Let's say I take one of these sides. Let's say this one, this side down here. Then I can rotate that to any side that I want. So I can rotate it, for example, to this side. But there are 6 sides, so that gives me 6 choices. So I can rotate this side to any side that I want. That gives me 6 choices. But once I put this side here, I can still rotate it like this, or like this, or like this, or like this. You see, once I fix a side, I still have 4 rotations left. So therefore, the group of rotations of a cube has 6 times 4 elements. But there are also 8 vertices, 4 at the bottom and 4 at the top. And any one of these vertices, I can rotate it to any other one. So for example, I can rotate this one in the back there. Well, that gives me 8 choices. Okay. And well, once I fix this vertex, for example, once I fix this vertex, then I still have 3 rotations left. Then I still have 3 rotations left, like this one and this one, that leave that vertex in place. So the symmetry group of a cube, you can move a face to 6 other faces, and then you still have 4 rotations left, or you can move a vertex to one of 8 vertices, and then you still have 3 rotations left. So the group of symmetries of a cube must have this many elements, but must also have this many elements. And fortunately, those 2 numbers are the same. Both of these are 24. Okay, but now these angles and these rotations, this is very common in ordinary construction. Like if in ordinary buildings, many things have 90 degrees angles, just like what you see here. Like the walls and the floors have 90-degree angles. One floor to the other floor has 90-degree angles. The struts, that hold things that carry all the weight. Like a lot of things have 90-degree angles to each other, and just like in the cube. But now the question is there some other type of construction based on the symmetries of something other than this? Okay. So the more symmetrical something is, the more symmetries it has. Like this is a highly symmetrical object, and you can rotate it in 24 different ways, and it will still look like this. Now, what other highly symmetrical objects are there? Well, they've been known for a very long time. They're called the Platonic solids, and Plato lived a long time ago, so the highly symmetrical solids have been classified a long time ago. Well, there's the cube, which you just saw, and it has a symmetry group called S4 with 24 elements. I calculated that, right? 24 elements. Then there's the octahedron, but it has the same number of elements. For example, you see this one has 6 vertices, but once you fix a vertex, like this one, then you still have 4 rotations left, like this one and this one. So this one also has 6 times 4 elements. So is that, maybe that's a bit of a coincidence that we end up with the same group, but it's not really a coincidence. You see, this thing has 6 sides and 8 vertices. And this one has 6 vertices and 8 sides. So that gives you an idea. What if in the middle of each side you drew a vertex, like here, 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 here. So then you get 6 vertices. And those vertices form an octahedron. So if you put a vertex on each side here, then you get this. But if you do the same for this one, if you put a vertex on each of the 8 sides, then you get the 8 vertices of a cube. So these objects are called dual. If you swap vertices and sides, then one goes to the other, and that's why they have the same group. So that's why I won't look at the octahedral group of symmetries, because it's the same as the ones that we already looked at. Now the same goes for the dodecahedron and the icosahedron. They are each other's dual. If you replace vertices, if you swap vertices and edge and faces on this one, you get this one. So they have the same symmetry group, and that group has 60 elements. Well, how do I see that so quickly that it has 60 elements? Well, for example, this one, it has 20 sides. So this side can be rotated to any other side. Or for example, this side can be rotated to this side or to any other side. But once I fix this side, I still have 3 rotations left, because I can leave it as is, or I can rotate it 1/3 of a turn, or I can rotate it 2/3 of a turn. So this group has 20. There's 20 sides, and each side can be rotated to any other side. But after you do that, you still have 3 rotations left. Now, this one, it also has 12 vertices. And any of these vertices can be rotated to any other vertex. But once you fix a vertex, like this one, then there's still 5 rotations left, because if I rotate this 1/5 of a turn, it looks the same. So the group also has this many elements. 12 choices for where the vertex goes, and then 5 more rotations left. And fortunately, this is the same problem. So the octahedral group and the dodecahedral group, they are both groups with 60 elements, and the names of these groups is A5. Well, then there's also the tetrahedron, and this one, I'll leave this as an X. Okay, you have 4 sides. So this side on the back, I have 4 choices where I can go to. For example, I can rotate it over there. And once I fix it, I still have 3 rotations. So this group has order 4 times 3. But these rotations form actually a subgroup of these rotations. So therefore, this one is way more interesting than this one. So the group of rotations that we're going to consider is the group A5, the set of rotations of the dodecahedron, and also the set of the rotations of the icosahedron. Now there are 15 rotations of order 2. Okay, there are 20 rotations of order 3 in the group A5, and there are 24 rotations of order 5. But if you have an order n rotation, then that will be a rotation along some axis. Okay. Now, along this axis, I have 4 elements of order 5. I can make 1/5 of a turn, or 2/5 of a turn, or 3/5 of a turn, or 4/5 of a turn. And any one of those operations is something that has order 5, meaning you have to, if you make a 4/5 of a turn, you have to do that 5 times to get back to where you started. If you make a 3/5 of a turn, you have to do that 5 times to get back to where you started. So if you have 4, so for each axis, I have 4 of these order 5 rotations. And since I have 24 of these rotations altogether, that means I have 24 divided by 4 is 6 axes that correspond to order 6 rotations. And likewise, there are 10 axes that correspond to order 3 rotations and 15 axes that correspond to order 2 rotations. So I have a lot of axes of rotations, 15 plus 10 plus 6. Now, what am I going to do with these axes of rotation? So imagine taking all the rotations that come from this, but applying them to a sphere, like a solid ball, and rotate it and apply these 60 rotations. Okay, we have rotations of order. We have rotation axis of order 2, rotation axis of order 3, and rotation axis of order 5. Let's say we pick the rotation axis for an order 2 rotation. So that's like an axis that goes through the ball. And you want this rotation axis, you want to be able to put it through the ball. So you take this ball and you drill holes in the ball exactly where the rotation axis intersects with the sphere. Okay, that's where you drill holes. But order 2 rotations, you want to drill holes there that have an order 2 symmetry. So you drill rectangles in those along those axes. So let's say here's that ball. If you see an order 2, if you have an axis of rotation of order 2, then along that axis you drill rectangular holes like this one and this one in the back. Okay. Now for every rotation of order 3, you drill a hole with a symmetry of order 3, namely a triangle. And for every rotation axis for rotations of order 5, wherever those axes cut through the sphere, there you drill a hole with a symmetry of order 5. And if you drill the holes that way, the result is called a zone ball. And I'll hold one up close to the camera. So for example, here you're looking through at a hole of order 5, and here you're looking at a hole of order 2, and then these triangles are holes with a symmetry of order 3. And so how many holes are there altogether? Well, we had 15 blue axes, and each blue axis cuts through that sphere on 2 sides. So we have 15 times 2 rectangular holes. And then we have 20 over 2, we had 10 rotation axes of order 3. And each cuts through the hole and cuts through the sphere on 2 sides, and in each you cut a triangular hole. So we have 20 triangular holes. And then we have 6 axes of rotation of order 5, and in each you drill a pentagonal hole on both sides. So that means you have 12 of those. So we have 12 holes of order 5, 20 holes of order 2, and 30 holes of order 3. Well, now to get a construction toy, I need to have things that fit in those holes. Okay, so we're going to have blue struts that at the end have a symmetry of order 2. If you look at the connection, the connector at the end, that's a rectangle. So the blue struts have a rectangular connector, and they fit in the holes that correspond to symmetries of order 2. And then the yellow struts, they have a connector that's a triangle. So the yellow struts, they fit in the triangular holes that correspond to rotation axis of order 3. Okay, and then the red struts, their connectors are pentagons, and so those connectors fit in the holes with the symmetry of order 5. So anytime you see a blue strut, it's in the same direction as some axis of an order 2 rotation. Every time you see a yellow strut, it's in the same direction. It's aligned with a rotation symmetry of order 3, and any blue strut is aligned with a rotation axis with rotations of order 5. Okay, so anytime you see blue, think symmetry is order 2. If you see yellow, you think rotation of order 3, and if you see blue, red, you see that's a rotation of order 5. So now, what is blue space? Well, blue space are all the points you can reach using just blue struts. So off goes this red and this yellow. So imagine that we're in a three-dimensional space and we pick one point as the origin. So one point is, say, 0. So let's say that's this point. Okay. And now I can start building things. You see, I can put another zone ball on here. And then this has a bunch of holes with symmetry of order 2, and all of those holes fit blue struts. So I can fit a blue strut in here, for example. Now I'm going to declare one point to be the origin, this here. And then every vertex I can reach, the set of all those vertices combined is called blue space. But let's first imagine something simpler. Imagine that we only used blue struts in only the x direction, the y direction, in the x direction, the y direction, and the z direction. So we're only using. So imagine you're only using struts of length, say 1. Let's call this one length 1, and you're only allowed to go either straight left or right, straight forward, backward, or straight up and down. Well, in that case, the only reachable points are the points with integer coordinates. Okay, so if I only use this, then I get only integer coordinates. Now, if I allow the other holes as well that have some kind of angle, like this one, well, then obviously I can reach more points. Now, which points can I then get? Well, let's call that set capital B1. So capital B1 are all the vertices that you can reach with just blue 1 struts. Now it turns out that that's if I don't use just x, y, z directions, but I also use these angle directions, I can reach way more vertices. Namely, I can reach every vertex whose coordinate is a golden integer, but actually even a little bit more than that still. However, the only ones that I can reach is if v is something you can reach with blue 1 struts, then the coordinates of 2v are golden integers. That's what this subset means. And this subset means that if you have a vector whose if all of its entries are golden integers, then it can be reached with blue struts. Now, this set B1, the set of all points that you can reach with just blue 1 struts, there's a fancy math word. It's called a z-tau module. I'm not going to explain what that means. I'm just going to say the simple interpretation. If I say that this is a z-tau module, that means that if you take an element of it and you multiply by tau, then it's again an element of B1. So this means if you can reach some vector with blue 1 struts, then tau times that vector can also be reached with blue 1 struts. Okay, that's what it means. But if I want to be really fancy, then I'll say that B1 is a z-tau module. But really, I just mean this. Okay. So now, if you open a zone box, there are struts of different lengths. So there's not only the short blues, there are also medium blues, and then there are long blues. Okay, but really, how long should they be? So let's say I call this one length 1. How long should the other one be? Well, let's go back to this fancy word. Anything that's reachable with this, if you multiply by tau, it's still reachable with this. So in particular, tau times this is a distance that you can reach with just blue ones. So how about we make blue 2 the second biggest blue strut? How about we just make that tau times B1? Then the blue 2 strut can be reached with just blue 1 struts. And here's an example. This is a blue 2 strut, and you can see that this distance can be covered with blue 1 strut. So I have to take an angle. I can't just go straight, because then I can only, if I only go straight, then I can only reach these points. That's not very interesting. So so a blue 2 strut can be reached with blue 1 struts if I make blue 2 to be this here. Well, then let's do the same for the big one. Let's make B3 equal to tau times B2, because then this distance can be covered with 2 blue 2 struts, but every blue 2 strut can be covered with blue 1 struts. So I can also go from, with using blue 1 struts, I can also go from here to here. So I have two definitions. B1 is what you can reach with just the small struts, the small blue struts, and B is the set that you can reach with the small, the medium, and the large struts. But because B2 and B3 are in B1, ultimately the reason is because B1 is a Z-tau module. That's why these two sets are the same. So anything that's reachable with any of the blue struts is reachable with just blue 1 struts. So that's blue space. Well, now, but you see, the blue space, it only uses these symmetries. You know, the ones that were rotations of 180 degrees. You see, there are more symmetries, and there are more holes in these zone balls. So in these holes, we can fit these pieces. But now the question is, how long should they be in order to work well together? So let's investigate that for a moment. So when does a construction toy work well, and when does it work poorly? So let's look at the Lego example. Suppose you're building a Lego house, and you have bricks that are a size length 1, and you have bricks of length 2. Those bricks work pretty well together, because you see, if I pick a random number of the bricks of size of length 1, then I get some length in here. And if I pick some random element of this set, the chance it's in the other set is 1 in 2. And we'll call that the index. So we'll say that this set has this set is a subset of this set, and we say it's a subset of index 2. And the index 2 means that if you pick a random element of the bigger set, then the chance it's in the smaller set is 1 in 2. But that's a pretty big chance. That means you don't have to try a whole lot of times before you find something that fits. I mean, if you don't pay any attention to what you're picking at all, then you already have a 50% shot. So if you pick some completely random element in here, you already have a 50% shot that the distance can be covered with the length 2 bricks. So in this example, the index is small, which means that there's a high chance that things fit together. So a small index is good for construction. You have a high chance that things fit together. Now, why don't we build Lego bricks with Lego houses with bricks of length 13 and 17? Imagine that's you bought this Lego house, and those are the only bricks that are in there. They have length 13 or 17. Well, if I now pick a random number of these bricks, the chance that it's the same distance can be covered with these bricks is quite small. So if I look at all the lengths that could be created with the bricks combined, then these bricks have a high index in there. Meaning, if I have some wall made with the two of these bricks, the chance that it can be covered, the same distance that can be covered with just these bricks, is quite small. So that's why these bricks don't work well together. It's very unlikely that by trial and error you're going to get things that fit, because the index is so high. So high index means low chance that random things fit together, and low index means there's a high chance that things fit together, even if you chose them at random. Okay, so we want we want the index to be low. If the index is low, then things will often fit, even if we don't pay any attention to what we're doing. Okay, if we just pick some random element. Okay, so now let's introduce yellow space. So let's say we pick some yellow strut of some length, but we have to still determine what that length is. Now, since blue 2 is tau times blue 1 and blue 3 is tau squared times blue 1, let's do the same for yellow and red. So if the small yellow is this, then the next yellow is tau times bigger, and the next yellow after that is still tau times bigger. And then we do the same for red. We pick some length of red, yet to be determined, but the next length is tau times bigger, and the next length after that is still tau times bigger. So by the way, you never really need the longest struts, because 1 plus tau is tau squared. So if you run out of these long ones, you can make one by putting a small and a medium together. See? So this one has length 1. Let's say this length 1, length tau squared, but 1 plus tau is tau squared. Okay? So these really long ones are really just for convenience, and if you ever run out, you just use the small and the medium ones. Okay. So now let Y be the set of all points reachable with yellow struts. So that means I'm going to pick some zone ball, and I'm going to declare that to be the origin. It has coordinates 0, 0, 0. And now you can only use the yellow openings, the triangular openings, and you can put these yellow struts in there, but you may use any of the yellow openings that you want. And there are quite a few of them. You see there are this many axes of rotation of order 3, and each has 2 holes, so that's 20 holes altogether. So with yellow, just like blue, you can reach quite a lot of points. And let's say that Y is the set of all points reachable with yellow struts. Now, if I want to be fancy again, that's automatically a z-tau module. The reason being, but that's more like by construction, the reason being because if I have a yellow 1, then I can also reach tau times that. And if I have a yellow 2, then I can also reach tau times that. But what about yellow 3? Well, yeah, if I multiply this by tau, it will still be a linear combination of in some integer times yellow 1 plus integer times the yellow 2. Okay, so this set Y is automatically a z-tau module. If you have anything in there multiplied by tau, then it's again reachable. The question now is, how long should the base yellow be in order for the yellows to fit well with the blues? So what you want is the index between the blues and the yellows. You want this index to be as small as possible, because if you have a small index, then things will fit well together, even when selected randomly. And if you have a high index, if you select things at random, it's very unlikely that they'll fit together to make okay. So we want a low index, and minimizing the index gives you only one value of tau. Well, actually, it gives you one value of tau, except that you may still multiply by any tau power. So if you want to minimize the index between blue and yellow, then then every yellow strut, the length must be this number times a tau power. But it doesn't really matter which tau power, because you see, if I'm making Y1, I'm also making tau times that. So this is not so important. So the thing is that the yellow struts must be this number times tau powers. That will minimize the index. And the red struts must be this length times tau powers. That minimizes the index. And well, what index do you end up getting? With the blue 1 struts, you can reach all vectors whose coordinates are golden integers, but you can reach a little bit more than that. In fact, the index between this set and this set is 4. Now with the blue 1 struts, you can reach the same vertices that you can reach if you use all the struts. If you minimize the index, which I explained to you is best, then the yellow struts reach a little bit more vertices than the blue struts. And here the index is 4, and that's as small as you can make it. Okay, so yellow struts can reach a little bit more vertices than blue struts. Okay, the index is 4. Now with the red struts, if you take it this way, they can reach exactly the same vertices as the yellow struts. So everything that's reachable on the red is reachable on the yellow, and everything that's and that's the same. And finally, everything that's reachable on the red, the coordinates of that will be a Gaussian integer. A golden integer, possibly divided by 2. And again, the index from here to here is 4. So here we have an index 4. Here we have an index 4. Here we have an index 4. And if you know that z tau is a PID, then you know that the index can't be smaller than 4. That's the minimal. So this is optimal. Okay. So yeah. Now let's talk about Zohm space. So Zohm space is so you fix one vertex at the origin. Just imagine you glue that in place so that it never moves again. And then Z is the set of all points you can reach with all of the blue Zohm struts combined, with the yellow ones and the red ones and the blue ones. Okay, so let's call that Z. That's Zohm space. Now Zohm space, you see, because red contains yellow and yellow contains red and both of them contain blue, that means that the red space contains all the others. And so does the yellow space. So the Zohm space is equal to the yellow space and also equal to the red space. And the blue space sits in there with index 4. And this is optimal. Now, what does that all mean, this index 4? It just means that if I pick elements at random, the odds that it's going to fit is basically 1 in 4. That's what index 4 means. So so let's say I have some zone construction, but now I look at it and think, well, there's a lot of blue and yellow here. There's no red. So let's make this thing a little bit more interesting. So let's say I pick some vertices, like say this one and this one, and I want to make another connection from here to here. There's already a connection, yeah, via a medium blue and a short yellow. So let's make another. So let's pick some random pieces, and I want to go from. Let's see, make sure it's good. I want to go, say, from this one to this one, and I just pick my pieces at random. Let's take these 3. Okay, so well, this takes me in the right direction, right? And then I try this one, and doesn't quite fit. Well, maybe if I stick this in a different direction, and then go like this, well, it also doesn't quite fit. So the point I'm trying to make is that if I want to go from this vertex to this vertex, and I'm selecting these struts at random, then I have a 1 in 4 chance that I can go from this vertex to this vertex. And that's basically what index 4 means. But now people say that zometool things tend to fit pretty well together because, well, a 1 in 4 chance isn't terrible. I failed to do this, but if I pick some other random pieces, if I do this 4 times, then chances are that at some point it's going to work, right? So it's not a whole lot of times that I have to try things out before I can make a new fitting connection from here to here. But we're mathematicians. Maybe we can increase those odds, those 1 in 4 odds. maybe if I pick my, instead of trying out a bunch of different pieces and see if I can get a connection from here to here, maybe there's a way to beat these odds. Okay. So right, and that brings me to the next concept, labels. Okay. So let's fix this thing at the origin, right? And remember, all the vertices you can reach with just blue vertices, that's blue space. But that's not all of Zoom space. It's basically 1/4 of that, right? Because the index is 4. And now I'm going to do the. Now here is something that isn't in Zoom space, in blue space. For example, yellow one is not in blue space. It's not. This cannot be covered with just blues. So how about we do the following now? Let's call this vertex V. So here is 0. Then here is vertex V. Now imagine you make a set Z, let's call that set Z1, which is all the vertices that you can reach if you start from this one and use just blues. So so Z1 is all the vertices that you can reach with 1 yellow, and then the rest as many blues as you want. Now Z0, let's call that blue space. It's everything you can reach with blue. So this is everything you can reach with blue. This is everything you can reach with blue plus 1 short yellow. And then Z tau, let that be the set of all points you can reach with 1 medium yellow and then as many blues as you want. And then Z of tau square, yeah, tau square is tau plus 1, is anything you can reach with a big yellow and then as many blues as you want. Okay, so now I've divided up Zoom space into 4 subspace, into 4 subsets, and the union is all of Zoom space. Okay, so I've split it up Zoom space into 4 pieces, and in math those pieces are called cosets. Now, what does the word coset mean? A coset means that you take one particular vector, and then to that vector you add every vector in this set B. Okay, so a coset is we have one particular vector which is either say 0 or yellow 1 or yellow 2 or yellow 3, and then to that vector you add everything in this set. So we have 4 cosets, and Zoom space is a union of those 4 cosets. So any element of Zoom space is either in here or in here or in here or in here. Now, if an element of Zoom space is in here, then I'm going to give it label 0. So everything that you can reach with blue will get label 0. Everything that you can reach with a short yellow and then blue is going to get label 1. And everything you can reach with a medium yellow and then the rest all blue is going to have label tau. And everything that you can reach with a long yellow and then the rest all blues is going to get labeled tau plus 1. So now every element in Zoom space will get a label. The label is either 0, 1, tau, or tau plus 1. Now, elements of Zoom space are vectors that you can add, right? So if I have this vector and this vector, I can just add them by just connecting them, right? So you can add elements of Zoom space, okay? Now, what happens if you add labels? Well, here I have yellow 1 added to another yellow 1, right? So this distance is 2 yellow 1. But notice that this distance is also can also be covered with blues. You just follow this one and then this one and then this one. So 2 times yellow 1 is in blue space. So 2 times any yellow vector will have label 0. And I added some additional blue struts to make this thing more rigid. So the more rigid you make something, the less it can bend, and the easier it is to see that a gap is either 0 or non-zero. Okay, so this here, remember I said earlier, the gap theorem allows me to view Zoom constructions as mathematical proofs. So this here, if the gap theorem is correct, then this object is a mathematical proof that 2 times yellow 1 does sit in blue space. And the same is also true for 2 times red 1. You see, red 1 plus red 1 is a distance that you can cover with blue. So, and since Zoom space is made from blue, yellows, and red, that means that everything in Zoom space, if you add it to itself, you get 0. So the sum of a label plus itself must always be 0. And that means you're working modulo 2. So whenever you see something that's 2, you should think of it as 0. So basically 0 and 2 and 4 and 6, you should think of this as all the same. So just let's just call this as even. Okay. And then 1 and 3 and 5 and 7. If you work modulo 2, then all of these are the same. And let's just call that all. So the labels really are even times 1 plus even times tau, or odd times 1 plus even times tau, or even times 1 plus odd times tau, or odd times tau plus odd times 1. Okay, those are the 4 labels. And now, how would you add labels? Well, let's say you have 3 vectors, and they have length label tau plus 1, and tau plus 1. So how would you add them up? If you initially add them up, it's like this. But you should think of all even numbers as basically the same, and all odd numbers as basically the same. So modulo 2, if you have 3 tau plus 2, then the 3 is the same as 1, simplifies to 1, and the 2 simplifies to 0. So that's called modular arithmetic. You can working modulo 2 means you can always add or subtract any multiple of 2. So if you add or subtract any multiple of 2, then this simplifies to this. So if the labels are, if you have 3 things with these labels, then the sum of these vectors will have this label. Okay. Now you can also multiply labels by tau, because, for example, let's say if you have a label with if you have a label tau plus 1, if you multiply that by tau, you get tau squared plus tau. But tau squared is the same as tau plus 1. And now we have 2 tau plus 1, which simplifies to 1. So if you have this label, so if a vector has this label, you multiply that vector by tau, then the label will be 1. Now let's look at closed loops. If I take this vector plus this vector plus this vector, then I get back to where I started. So the sum of these 3 vectors is 0. But the label of 0 is 0. So then the sum of the labels must also be 0. And again, I view this as a mathematically valid proof, this thing that I'm holding in my hand. Okay. So in a closed loop, the labels add up to 0. But blue always has label 0. So the label of this one and the label of this one, they must be the same. Okay. That means the label of this vector and the label of this vector. These 2 vectors have the same label. Now, you may have once heard that a degree 5 equation there's in general not a formula to solve it. You cannot reduce a degree 5 polynomial equation, at least in general. You cannot reduce that to, say, a degree 4 equation. And on the Galois theory, the underlying mathematical reason for that is because the group A5, you see this 5 here is that 5, that the group A5 cannot non-trivially permute 4 objects. So if you have A5 working with a set with 4 things, the only thing it can do is send each thing to itself. Now, here we have 4 objects. We have Z0, Z1, Z tau, and this. So we have 4 objects, but our symmetry group is the set of all rotation. That's where we started with. We started with things that are symmetric under these rotations, and that group is A5. But so A5 must permute these four things. However, A5 cannot permute four things in a non-trivial manner, which means that rotations send things in here to things in here. It sends things in here to things in here, and it sends things in here to things in here. That means that the label of this guy, you see, if I rotate this vector, I can get, for example, this vector. Okay, this vector, since this vector can be rotated to this under an action of A5, but since A5 cannot act non-trivial on four things, that means this label must be the same as this label. Okay, so A5 rotations cannot change the labels because there's only four labels, and A5 cannot non-trivially permute four things in any way. So that means that the label of this vector and the label of this vector is the same. So that means that the struts themselves have labels that are independent of which direction they're pointing. So now I can figure out the labels for each of the struts. Well, the blue struts have label 0, and the short yellow struts, well, let's call that label 1. Then the medium yellow, well, that's tau times longer, so it will get labeled tau. And then the long yellow is even tau times longer, so it gets labeled tau square, which is tau plus 1. But now this is a closed loop, so this label plus this one must be 0. Well, this has labeled tau plus 1, this has labeled 0. Then this one must also have labeled tau plus 1, because tau plus 1 plus tau plus 1 is 2 tau plus 2. But 2 plus 2, if you work modulo 2, that's the same as 0. So the short red gets the same label as the longest yellow. Now the medium red is tau times longer. Now if you multiply this by tau, and if you then reduce modulo 2, you get 1. And if you multiply again by tau, you get this. So these are the labels of the red struts. Okay. So now every strut has a label, and if you have a closed loop, the sum of the labels is 0. But keep in mind, if you have a sum of labels, you must first simplify that, right? Every odd number simplifies to 1, and every even number simplifies to 0. And in that case, anytime you have a closed loop, the labels add up to 0. Okay. So, well, now I have an explanation for why. Remember, I try to make a connection from this one to this one, and I just didn't know how, at least at first. So I just took some struts. I took these ones. This one has length 0. This one has length 0. And this long red one, it has label tau. Okay. So tau plus. So I took these struts, try to go from here to there, but the sum of these struts is tau. But now let's look here. How do I go from here to here? Well, I can walk over this blue strut that has label 0, and then this yellow 1 strut, and this yellow 1 strut has label 1. Okay. So to go from this vertex to this vertex, right? Oh yeah. So to go from this one to this one, I must have a collection of struts whose sum is label 1. And when I randomly selected some struts, I had some struts whose sum is whose sum adds up to this. Okay. So well, how about okay, so if I have this strut tau, let's take one of these struts. That's tau plus 1. Tau plus 1 plus tau is 2 tau plus 1, which is the same as 1. So if I pick one of these struts plus one of these struts, then the label is 1, and that's the same as the label between here and here. So now I'm just taking two struts whose label sum is the same as the label sum between as the label difference between here and here. And now let's see. Wait. Let me see. Oh. Okay, let's put this one over here. Okay, and remember I'm trying to go from here to there. Let's put this one over here. You see? That's now that I picked the two, these two struts are almost selected at random. The only condition that I looked at when I selected these struts is that they're long enough to go from here to there, and that this the label sum is the same as the existing label sum from a path from here to there, which is 1 plus 0. Okay, so the only thing I looked at is, okay, they're long enough, and the sum of the labels is the right one. And lo and behold, it just fits right away. See? So this is the perfect amount of space to fit in a zone ball. So okay, so yeah, so let's see. So if I have some construction made with a zone and I want to make another connection from some point to somewhere else, if I just pick my struts at random, right? Let's say I take well, let's say I take a short yellow, a short red, and a medium yellow. The odds that that's going to allow me to go from one point to the other is 1 in 4, and that's because the well, let's add another blue, for example. Okay, the odds that if I have two zone points and if I can cover the distance with this, but the odds that it's actually going to fit is 1 in 4 because the index is 4. However, if I take some struts with the correct label sum, the odds that it's going to increase fit increases by a factor 4 because there are 4 different labels. So if I randomly try to fit things in zone, the odds that it's going to fit is 1 in 4. However, if the label sum is correct, the odds are 4 times higher than that. So this brings me to the following theorem. So the label theorem. So take at least 3 zone struts, and well, here I'm only considering the blues, the yellows, and the reds. Now, when do these n struts fit together in a closed loop? Okay, so let me first give you a few examples that don't fit in the closed loop. Let's say the longest one is longer than some of the other ones combined. Now, obviously, I can't make a loop out of that. Okay, so if this one is longer than some of the other ones combined, I can't make a loop out of that. I don't want the longest one of the n struts should be shorter than everything else combined. This is something I'll explain on the next slide. And I need the sum of the labels to be 0. And if those 3 conditions are all met, then so for any n greater or equal 3 zone struts, if these 3 conditions are met, then all those n struts fit together in one loop. So this is an if and only if. If any of these conditions fails, like for example this, then you cannot fit them into one loop. Just like I was trying to make another a loop between here and there, but in the first example I picked the wrong label sum, then it will not fit. So this here is a necessary and sufficient condition. But you might wonder, yeah, what on earth are conjugate lengths? I mean, vectors have lengths, right? So yeah, what's a conjugate length? So let me give an blue space and zone space consist of vectors such that if you multiply them by 2, then all the coefficients become golden integers. And in particular, all the coefficients can be written so inside this vector space. So all the coefficients can be written in terms of square root of 5. But if you multiply a bunch of things with, let's say you have an equation where on the left side you have multiplied a whole bunch of numbers together with square root of 5s in there, and on the right side you multiply together a whole bunch of other numbers with square root of 5 in it. If you replace square root of 5 by minus square root of 5, the formula will still hold, even though all the numbers changed. And that's called conjugation. So you just replace the square root by minus the square root. I'm gonna denote that with v bar. So if v is a vector, and then v bar is the vector where every square root of 5 you see, you replace it by square root of 5. Now, if I have a closed loop, then I have a bunch of points, right? If I conjugate everything, it's still a closed loop, except that it will look totally different, but it's still a closed loop. Now, in any closed loop, the longest should be shorter than the sum of the rest. So you see, this object right here, if I take all the conjugate lengths, then that should still fit together. So here, the longest one is shorter than the sum of the other two. In the conjugate lengths, that must still be the same, because otherwise, after conjugation, I don't have a closed loop. But conjugation will send a closed loop to a closed loop. So since I have a closed loop, after conjugation, I have a closed loop. So the conjugate lengths, the biggest one, must still be less or equal than the rest. Now, what are conjugate lengths? The length of b1 squared is 1. If I replace square root of 5 by minus square root of 5, nothing changes. So the conjugate length of b1 is still the same as before. The length square of yellow one is 3/4, but there's no square root of 5 in there. So if you conjugate, it stays the same. So yellow one conjugate length is the same. Now, red one square, the length square of red one is this number, but that has a square root of 5 in it. So if you conjugate it, it changes. It gets smaller. So red one, if you conjugate this vector has length R1. If you conjugate it, then the length square will be this. So that means the actual length will be tau inverse times what it was before. And let's call that R0 because it's short. R0 is a strut that's a factor tau shorter than R1. So that's so those are really short. Now, why would R0s, these really super short ones, why would they be useful? Well, because they occur naturally on the conjugation. That's why they often fit. So now if I take a longer one, this is tau times b1. Well, the conjugate of tau is -1 time, but under absolute values that disappears. The conjugate of tau is basically tau inverse, times the minus sign. So every time you multiply with tau, then the conjugate length. So if you make a vector tau times longer, then the conjugate length becomes tau times shorter. So the conjugate length of b2 is basically b0, and the conjugate length of b3 is b-1. It's basically this length divided by tau squared. But I don't have things that are that short. So what I do is after conjugation, I just multiply by tau squared to scale it up to things that I have. And if I conjugate and then multiply by tau squared, then conjugation sends b1 to b1. If I multiply by tau squared, it goes to b3. Conjugation sends b2 to something, this divided by tau, and then multiply by tau squared, then I go here, etc. So conjugation basically swaps b1 and b3 and leaves b2 fixed. It swaps y1 and y3 and leaves y2 fixed, but it sends y1 to r1 to r2, r2 to r1, and r3 to r0, which wasn't part of Zom originally, or r0. So this is how conjugation acts. So now let me give you an example. So here. So let's consider these three struts. I have two long reds and a short blue. Now, if I take the longest one, it is not longer than the sum of the rest combined. Okay? So the first condition is met. Right? The longest one is not longer than the sum of the rest combined. The sum of the labels is 0 because I have two reds of the. If you have a strut and the same strut, if you double a label, it's always 0. So the sum of these two labels is 0, and this also has label 0. So the second condition is also met, and yet if I try to build a triangle out of that, I can't. Now, what is the explanation for that? You see? So let's build. Yeah, you see. Yeah, you might say, well, you can't build a triangle out of that because this one is too short. But that's not okay. Yeah, that's not really a good explanation. See? So the issue is that if you conjugate these things, what happens if I conjugate these? Well, then the long red becomes a really long red becomes a really short red. So if I conjugate these, then I get these really short reds. Okay, but if I conjugate this short blue, then I get a long blue. You see, and it's kind of clear that with these three pieces, you cannot make a closed loop because the long one is more than the sum of all the others combined. Now, since these do not form a closed loop, that means that their conjugates, which are these, okay, don't form a closed loop either. Okay, because if these form the closed loop, then the conjugate should also form a closed loop, but they obviously can't because the conjugates are two really short ones and one really tall one. Okay, so that's why this is also a necessary condition. But combined, this is a necessary and sufficient condition. So if you don't have like one ridiculously long conjugate length and the rest is really short, and if you don't have one ridiculously long Zohm strut and the rest is really short, and most importantly, if the sum of the labels is 0, then it will form a closed loop. Okay, so now this is incredibly helpful for Zohm constructions because yeah, when my son was about 5 years old, we were building these Lego trains, and then we wanted to have a bridge. So we had two tables and put a 6 feet gap in between, and then we built a bridge made out of Zohm pieces. But that bridge was 6 feet long, all made out of pieces like this. Well, how does something become strong? How does the bridge not collapse? Well, you have to make as many connections as possible, because the more ways things are tied together, the more rigid they become. So all throughout that bridge, whatever it is that could be connected should be connected. But with the label theorem, this is incredibly easy to do, because you just look at, oh wait, I want to connect this to that. Right. So let me see. So I just look at what connection is already there, just add up all the labels, then just grab some struts that have the same label sum, then you already know ahead of time it's going to fit. That's just a sure thing. And so this makes it way easier to build things with Zohm, because as long as you just quickly look at the label sum, if the label sum is correct, it is a sure thing that it will fit. So that makes building with Zohm very convenient. That's a pity that I don't have a picture of that Zohm bridge, but it was really, yeah, it was really something. It was really strong. We had like several tracks running over it, and it was all made very colorful because it was all made out of these pieces. So yeah, okay, but yeah, that's a long time ago. So Okay, so then finally, yeah, conjugate lengths also kind of explain what's going on with the gap theorem. You see, so first, let's consider a Gaussian integer. Okay, if you take a Gaussian integer and you multiply it by its conjugate, then you get an actual integer. Now, if your Gaussian integer is not 0 and you multiply it by its conjugate, then you get a non-zero integer. But a non-zero integer is at least 1. So the only way a vector can be close to 0 without being 0 is when its conjugate is really long. Okay, so if I want to find a zone construction where the gap is non-zero but as small as you could possibly make it, right? If you want this to be as close to 0 as possible, then you want the conjugate to be as big as possible. Okay, that's the only way you can make a vector really, really short. Okay, so if you make now by the way, notice that the short vectors, they are the ones that have the biggest conjugates. So basically, if you want to have a really short vector, you want the conjugate vector to be as tall as possible. Well, then you want to make sure you use a lot of these guys and these guys, because they are the ones that have really big conjugate lengths. This one a little bit less so, because R2 is shorter than R3. So if you want a really short vector, then the conjugate vector should be really, really long. That means the conjugate vector should use a lot of these guys. That means the original vector should use a lot of these guys. And that's why this here is the smallest gap you can create in Zoom using just two pieces, a short blue and a short yellow. But now, how long can a conjugate vector actually be? Well, let's say you used n zone pieces. Well, look at the longest zone piece you have, or at least among the conjugates. Well, that's this here. Okay. So the conjugate vector, how long can it be? Well, it can be at most, if the vector is made out of n zone pieces, the conjugate vector, the length it could at most be is n times some constant. So this thing, if we are using n zone struts, then this thing, this vector, is at most n times a constant. That means that this vector is at least a constant divided by n. Okay, so just thinking about conjugation and what conjugation does with vectors, you immediately find a version of the zometool gap theorem, namely, if you can construct a vector v with n struts, then either that vector is 0 or the vector length is greater or equal than a constant divided by n. Yeah. Now, how good can you make that constant? But it depends a little bit on how you compute, because you see a vector has 3 coefficients. Well, they're not quite in z tau. They are in elements of z tau divided by 2. Okay, but the same logic applies. Now, if the vector has 3 non-zero entries, then you can apply this logic to all 3 entries. And then you get a certain bound for how small this vector can be. But it turns out that some vectors, like the vectors in the red directions, they have 1 coefficient entry 0 and 2 coefficients non-zero. And after so for vectors in the red direction, I can apply this story not to all 3 entries, but only to 2 entries. And that's why for vectors in the red direction, the bound isn't as good as for all the other vectors. And indeed, this direction from here to here is in the red direction. Okay, so for vectors in the red direction, I mean vectors that have only 2 non-zero entries, I can apply this story only twice instead of 3 times, And so for those ones, the bound isn't as good as for everything else. And then for those ones, the constant that I found is 0.7. And that's pretty good because this gap is 0.36. And if you take 0.7 divided by 2, you get 0.35. So this gap is 0.35. And with the constant 0.7 that I found that this gap is either at least 0.35 or 0. Okay, the gap is obviously not 0, so the gap is at least 0.35, and it's actually 0.36. So that's pretty sharp. Okay, so so what I'm saying is this this theorem, if you replace this 0.7 by a bigger number, let's say 1. No. I mean smaller number. If I replace this by a smaller constant, let's say 0.5, then this becomes, or let's say 0.4 or something like that. Let's say if you replace this 0.7 by 0.3, then this is a really easy theorem to prove, and really everything you need to know for that is on this last slide. But then if you want to make this bound a little bit tighter, if you want to raise this number a little bit, then you have to do more computations. Okay, but yeah, again, if you replace the 0.27 by some smaller constant, then then all you really need to know is just conjugation, and then you can prove this zometool gap theorem. But of course, you should first prove prove this version instead during the problem session. And then I guess I'll stop here, and I get also my time is up.
Thank you very much, Mark, for this very nice lecture. It's a nice mixture of algebra and geometry.
Yeah, it's algebra by hand, like.
Yeah, exactly.
You just,
which is not something we can say every day.
So yeah, once I gave the yellows labels, I figure, well, how do I figure out the label for red? Should I do a bunch of computations? No, of course not. Just build a triangle, right? So that's really how that entry is computed. That's literally computed by this. That's not computed by a bunch of angles or cosines or whatever numbers. That's just the label for yellow 1. I just named that 1, and then yellow 2, yellow 3, just multiply by tau, and then the label for red 1 literally comes from this triangle. I mean, that's all. Yeah, but again, we should accept this as a mathematically valid proof, because either the gap is 0 or it's so large that it's obviously non-zero, and the latter is clearly not the case. So this is a mathematically exact fit. So it's a valid algebraic proof that those labels that are listed are indeed correct.
So there are some questions from the members of the audience. I'd like, before I read some of them, I'd like to take this opportunity to remind the members of the audience that you can type in questions, and I will be able to read them to Mark right now. So some of you have already done this, so I'll start right now.
Grab some more. I use a lot of yellow and blue. We also make fun stuff with red. Yeah. So so what's the first question?
So first question from Victoria. Why? It's an interesting question, I think. Why are symmetry groups S or A when you write them, and not other letters of the alphabet? Does it mean something?
Oh, the S stands for symmetric group, and so S4 is also all permutations of the set 1, 2, 3, 4. And that's also a group with 24 elements. So if you permute these 4 numbers, then this one can go to any one of these 4. So that's 4 choices. But once you selected where this one goes, then this one, there's 3 spots free where it can go. So this one can go to any of the remaining 3. Well, then this number Now you've used up 2 numbers, so this one can go to any of the remaining 2. And then once you decide where 1, 2, and 3 goes, then for 4, there's only 1 spot left. So all permutations of 1, 2, 3, 4, that's a set with 24 elements. And in some sense, this is the same group as the rotations of the cube. It has the same number of elements of order 2, the same number of elements of order 3, the same number of elements of order 4, etc. Okay, so that's why I use the name S4. And then the next natural group to look at is S5, which is all permutations of 1, 2, 3, 5, 4, 5. Now this has 5 factorial equals 120 elements. But this group has a well-known subgroup denoted A5, and A stands for, so S stands for the symmetric group, which means you're allowing, so in S4, you're allowing all permutations of 1, 2, 3, 4. You can hustle them around in any which way. And if you have 2 permutations, you can compose them and get another permutation. That's why this is a group. If you take all permutations of 5 numbers, you get a group with 5 factorial elements. Now this has a subgroup called A5, and the A stands for alternating. These are all the permutations that are quote unquote even. And an even permutation is one that you can arrange with an even number of swaps. So for example, if I take 1, 2, 3, 4, 5, if I swap 1 and 2, that's now I've used 1 swap, but 1 is odd. If I now make another swap, let's say I swap these 2. So this one goes here, and this one goes there, and this one goes there, this one goes there, and this one goes there. So the permutation that sends 1 to 2, 2 to 3, 3 to 1, 4 to 4, and 5 to 5, that's built out of an even number of swaps. And that's called an alternating permutation, or also an even permutation. And A5 is the set of even permutations. So there are odd permutations and even permutations. And the even permutations, there are exactly half of them. It's 60. So A5 is a group with 60 elements. And you have the exact same orders and the exact same, there's the exact same number, you know, the number of elements of order 2, number of elements of order 3, number of elements of order 5 is exactly the same as for the rotations of the dodecahedral group. So, now this is what's this group here is the smallest non-solvable finite group. Okay, this is the smallest non-solvable group. This also means that 5 is the smallest degree of a non-solvable of a polynomial that you can't solve in terms of radicals. So this is the first non-solvable group. It's the smallest one. So this is a beautiful group. It plays a beautiful role in Galois theory, but also plays a beautiful role with Platonic solids, which arguably are also very beautiful objects. And it leads, and this group also leads to the zometool construction toy. Like I explained, if you want to minimize the indices, and there's only one way to do that. So there's only one good construction toy that you can make with this symmetry group, and that's zometool, and that's why it's awesome, because it's unique, right? You cannot make this. Well, you can make it worse, but you cannot make it. If you want to make it good, it can only come out the way they came out with it. So,
thank you. There's more questions actually. There's been more questions have been coming in while you were answering this one. A question from Paul. I think to clear up the way you were counting rotations of a cube, say. And the question is, if a vertex of a cube has 8 rotations to the other vertices, are we also counting its initial position?
So, well, yeah, except that the argument, it doesn't matter which one you start with, right? So I can, so so I can pick any vertex to be. I can point my focus to any vertex. You see, because it will be whatever I'm going to say holds true for all of them. If I'm going to rotate this cube, then this vertex will go to one of the 8 vertices. But that's true for all of them. So you might as well pick whatever vertex you like best, and that vertex will go to one of the 8 vertices. But of course, this is also true for this one and for this one and for that one. If I rotate this vertex will go to one of the 8. Let's say it goes here, right? But once I've decided that I want to have a rotation that sends this one to this one, and it doesn't matter which of these. So pick any 2 vertices, right, in the cube. Pick any 2 vertices that you like. Call one of them A and call one of them B, and that might even be the same vertex. But so pick any vertex, call it A. Pick any vertex, call it B. Now let's say you say, well, I want to have a rotation that sends A to B. Well, you could have chosen B in 8 different ways. So if I'm sending A to B, since I have 8 choices for B, that's already 8 rotations. But once A is moved to the vertex B that I selected, there's not one rotation that does that. There are 3 of them, because once A is moved to the correct spot, like let's say that this is your preferred vertex and now it's been rotated to where you want it. Well, if this vertex is where you want it, that still leaves me 3 degrees of freedom, because I can just leave it as is, or I can do this, or I can do this. So once your preferred vertex goes to your preferred, so you can pick any preferred vertex that you like, and you can pick any preferred location. But once you've rotated to that location, there are still 3 more rotations that leave it in place. So that means that altogether, there must have been 8 times 3 is 24 rotations that send the cube to the cube. Yeah.
Yes. So in particular, in order to get that number, you are counting the initial position and viewing this as a trivial rotation.
Yeah.
All right.
So if the preferred vertex and the preferred location are the same, you could just not rotate at all. Or you could still, if the preferred vertex and preferred rotation are the same, preferred vertex and preferred location are the same, you could not rotate at all, or you could do this or this.
Yes, that's right.
So once the preferred vertex is at the preferred location, you still have 3 rotations left.
Very good. Now there's a question from Bekir, a very precise question relating to your to page 17 on your slides.
Oh, I see.
Bekir is wondering why, when we connect one vertex to another vertex, randomly selecting bars or struts on this page in your slides, the choice of which vertices to connect does not seem to have any significance in determining the probability of success. So why wouldn't the probability of success be 1/3, regardless of the choice of vertices to connect?
So this is this is kind of like an experimental observation backed up by math. So let's say, like, I'm building this big zone range, and there's a lot of pieces, and I want to make a connection from here to here, right? If I go to my zone, my box, and I just grab some struts and the lengths and all that, that's all fine, right? It's long enough to get there. And so let's say I take 2 struts, and it's long enough to cover that distance. If I don't look at the labels, if I just ignore that altogether, the odds that those randomly selected struts are going to give me a connection from here to here, there is essentially 1 in 4. That's basically so that means also that it's not always going to succeed right the first time, but you don't have to try many times before it succeeds. So this is an experimental observation among zone builders that it doesn't take all that long before you get it to fit. It's always very easy in Zome to make new connections and to make it fit in really, really fun ways. This is an experimental observation. But why? But the question is, like, why does it fit and why doesn't it fit? And the thing is that if the so for instance, if I want to go from here to here, well, that's red plus the same red, which is 0. So if I want to go from here to here, I need to have something with label sum 0. Otherwise, it's not going to fit. Now, let's say I want to connect something that goes from here to there. Well, let's look at this trajectory. Okay, if I want to go from this one to this one, well, then that's 1, 2, 3 reds. So that's 3 times this. But 3 and working modulo 2, 3 and 1 is the same. Basically, the label difference between this one and this one is 3 times this, which is this. Now, if I'm going to go to my zone box and I'm going to grab some pieces, what are the odds that I'm going to grab some pieces with this label sum? Well, that's only 1 in 4. That's why if I try this without the label theorem, and I just grab some pieces, like for example, like let's say I grab this one and this one, right? I just grab these at random. Well, the odds that that's going to work is 1 in 4. But if I now pay attention to the labels, the odds are going to be vastly higher. So the labels need to add up to this. So what I could do is I could, for example, take a long yellow plus a blue. You want me to try that?
Sure.
See?
If you have them.
Or I could take a short. Yeah. Okay. So I wanted to go from what was it, from here to there, right? So let me see. Okay. So oh wait, it actually the long yellow already fits on its own. I don't need any blues. So it basically already fits on its own. See? Now, if I had taken struts at random, the odds that the labels match up is only 1 in 4. Okay. So now let's say I wanted to go instead from this one to that one. Well, that's 1, 2, 3, 4 red ones, but that's even. So that's sum 0. If I take a bunch of struts that don't add up to 0, it's not going to fit. So, well, blues, of course, add up to 0. So let me just see and test this. It's kind of hard to build inside something else. But
so I have to improvise some zone building.
Yeah, but you see. But why do I even try this without? Why do I demonstrate this? And honestly, I haven't even tested that. And why does it fit right from the get-go? It's because if the labels are right, it's going to fit. That's just the way it is. And if you don't pay attention to the labels, then you have a 1 in 4 chance it's going to fit, right? So, yeah. So there's like, yeah, there's a bunch of things you can do. So let's say, I don't know, like say I'm building something like this, or let's say I want to just put something in the middle, like here. And now I put in a bunch of yellows, but now I want to go in a different way, not with yellows, but let's say with reds from here to there. Well, you know, I could do trial and error and start with this one, but like I said, trial and error, that's a 1 in 4 shot. And if I try it with this one and maybe some blue, it's not going to work, because this yellow 2 has this label, and this red 2 has this label. So that's not going to work.
Mm-hmm.
So so I could take, for example, wait, I need this. Huh? So I could take, for example, a red 1 and a red 2. This plus that adds up to tau. Yeah, and then it's going to work. See? So with this one alone and then some blues, I can't go there. But with this one and this one, I can. And by the way, notice that gap is exactly the size of a zone ball. So once again, this is a mathematical proof that the gap theorem tells me that this is a mathematically exact fit. Okay. See? So as you're building houses with doors and windows or train bridges or whatever, if you pay attention to the labels, it's always going to fit. If you don't pay attention to the labels, well, you see, the sum of the labels has to be 0 in every loop, otherwise it's not a fit. So yeah, so that's what maybe I didn't, I'm not sure if I addressed it fully, or but that's basically what this was meant to express.
I think this is a very nice answer. Yeah, there are some more questions. Here's a question from Tim. Why does tau times tau plus 1 equal 1 and not tau modulo 2?
Oh, tau times tau plus 1? Oh, well, let me... tau times tau plus 1, that's tau square plus tau. But tau square is the same as tau plus 1. So this is tau plus 1 plus tau. So this is 2 tau plus 1. But when you're working with labels, you're working modulo 2. So all the evens count as the same, and all the odds count as the same. So this is, now the way you write equivalences in math is, instead of writing an equal sign, you write 3 lines. This tells you that this is not literally the same as that, but up to what we care about, it is. Right? So 0, 2, 4, 6, that's all this is all the same labels, and these are okay. So 2 tau plus 1. So 2 is equivalent to 0 when you work modulo 2. So 2 tau plus 1 is the same as 1. So therefore, if you have a label of tau plus 1, like for example, this guy has tau plus 1, or this guy also has the label tau plus 1. If you multiply that by tau, the label will become 1. Okay.
Yeah.
So
very good.
Yeah. So it maybe a little more math. So this set here is called in mathematics, that's called a ring. And a ring means if you take 2 elements and you add them or multiply them, they will still be in here. So the sum of 2 Gaussian integers is a Gaussian integer. So not Gaussian integer, I mean golden integers. And so is the product. Now, now in math, if you say you want to work modulo 2, you write that like this. So in this, if you write this here, then that means you're going to think of 2 tau plus 1. You're going to think of that as the same as 1. Okay. So within this ring, you can simplify this to this. Now this here has 4 elements: 0, 1, tau, and tau plus 1. And this is what's called in mathematics a field. Meaning that you can add in here, you can multiply in here, but everything also has an inverse. For example, the inverse of this is that one, because this one times that one is that one. And the inverse of this one is that one, because this one times that one is that one. And the inverse of 1 is 1, because 1 times 1 is 1. So this is a set with 4 quote-unquote numbers that behave just like the ordinary numbers. You can add, you can multiply, and you can divide by 0. So this is a field with 4 elements. And really, what zone space really is, it's a vector space over this field of dimension 1. So that means, I mean, not zone space, I mean label space. So the point is that if you can also work modulo blue. So if you have zone space, modulo blue space, both of these are modules over this ring, but this quotient space where you work modulo blue, this quotient space is a vector space over this field, and it's the vector space of dimension 1. So therefore, this is a vector space with 4 elements. So labels can also be thought of as elements in a one-dimensional vector space, or they can be thought of as elements of a field with 4 elements. Yeah, so that's kind of like the mathematical structure behind labels. So by the way, one thing I want to mention is you might think that the claims in this talk that this involves like a lot of computations with sines and cosines and what have you not, but that's really not the case, because there is this website called the Atlas of Finite Group Representations, and it tells you all the ways that a finite group could, for example, rotate things in various dimensions, like in 3 dimensions. So if I want to know how the group A5 acts on the 3-dimensional space, all I have to do is I just go to the website, click on the group A5, and click on 3-dimensional representations. And actually, there are 2 of them. There's the one that I presented, and also its conjugate. So, but in any case, so the representation, all the data that I need is already there. So what I'm saying is that all these theorems are based on really quite little computation. It's mostly just algebra. Like, for example, the knowledge that A5 is a non-solvable simple group, and therefore it cannot act in a non-trivial way on the 4 labels. So therefore it sends labels, therefore it acts trivial on labels. Therefore, an A5 rotation that sends this to the same in a different direction, that must have the same labels. That implies that the struts themselves have individual labels. And that really makes it way easier to build things in Zone, because your odds that the things you're going to try to fit are going to go up about a factor 4. And they weren't all that small to begin with. The odds that they would fit are roughly 1 in 4. If you increase that by a factor 4, that's very satisfactory to build with this, because it's pretty much going to always fit. Yeah.
Yeah, that's a very nice answer. It's also a good motivation to go and study representation theory, which makes me happy, because representation theory is my own field of research. There are some more questions. Here's a question from Kuidan Go. Could you explain again how the length of the red and yellow struts are determined? Is it just by testing around, or was it something you could do more systematically?
So there are many ways to do this. So I'm not saying that the inventors of Zone did it this way. In fact, I would think that's rather unlikely that that's their strategy. So if you look at some, let's say you want to build something that involves, say, yellow, right? And whatever it is that your favorite object is to build, if you base the decision of yellow on your favorite construction, it's almost a virtual thing that it's a virtual guarantee you're gonna come up with the same way. So let's say that I built this cube, and I notice, oh, wait a minute, there's this symmetry of order 3, right? So let's drill some holes in there with a symmetry of order 3, and then stick something in here. Well, wouldn't it be nice if I could reach the center of the cube? So I'll just base my yellow length just on that. Just, because if I can reach the center of this cube, I can make this really cool thing where I have all these yellows sticking out, like, then I can build this. Now, wouldn't it be nice if I could make that? And let's say that was the basis for deciding yellow. the yellow lengths. You come up with the same thing. So let's say, you know, or let's say you started with yellow, right? Let's say you decided, no, yellow, this is my length wall. I'm going to start with yellow pieces. And after I develop yellow pieces, I'm going to develop blue. Well, now I look through here, if you look through these holes, you see that there's an ordered two symmetry axis that goes through this hole and this hole. So let's say I've decided that I want yellow. I want this length of yellow. Now, how long should blue be? Well, it would be nice. There's a rotational axis that goes through this hole and through this, and you know, straight through it. It would be nice if the blue fitted in here. So suppose you want to just be able to do this, and then and suppose that's the sole basis for deciding red, yellow, or blue. You would still come up with the same thing. The thing is that this one choice, it works so much better than anything else. You could have based your decision on 10 different things and they would have all come up the same way. So when I say index, I'm trying to make this a little bit more mathematical. Like, for example, why are your Lego bricks not of size 13 and 17? You know, it's hard to fit them together. Like they have sizes 1, 2, and 4, right? So I wanted to have some kind of mathematical basis of saying that one choice is better than another because the index is lower. But the thing is, this one choice is so much better that, you know, if your sole thing was, well, I want to be able to build this, you know, then you come up with the same answer.
Mm-hmm.
Or let's say you had a nice octahedron, and you wanted to build something that can go from here to the center. And so instead of building this, let's say we do the following. We start with a zone ball, and we just stick in, let's say, a whole bunch of red ones, right? Okay. So let's say you take a zone ball, and every symmetry 5 hole, you stick in the red one. So you completely fill it up. But then you notice that, wait a minute, going from here to there, there's an order 2 symmetry. You see? Order 2 symmetry.
Mm-hmm.
So that means, well, wouldn't it be nice if I could go with a blue one from here to here? And let's say that that's your sole motivation. You just want to think of this thing as a, how you call it, a thing to prick in as many red needles as you can. Every red hole that you see here, you want to fill that up. Then you have all these pokey things. You think, well, it would be maybe nicer if I now added some struts here. And that determines the relation between the red length and the blue length. And this will also, once again, come out the same way, because like I said, that one way is so much better than every alternative that no matter what you base your decision on is always going to come out the same way as Zoom. And this is also what makes it impossible for me to guess what the basis was of that decision, because it really doesn't matter. It would have come out the same way.
Yes, it's a very robust process. We have time for maybe one more question, and it's a question about how to go further in this topic. Would you have any recommended further reading?
Oh, well, these slides, that's all there is. There's no, these slides, that is the publication. So that's really all that's written about this, at least as far as what I have presented in the talk. Now, there are some other books about Zoom, but they don't have these theorems. Like I bought a Zoom kit at a conference in 2006, and then a week later I emailed them all these theorems, and they hadn't heard of any of these. So so there are some Zoom books, but they won't have any of this in it. So I think maybe they came more from the construction side of things, and I'm looking at it more from the algebra side of things, like z-tau modules, you know, quotient spaces, you know, working modulo 2. I'm thinking more like an algebraist. That's why I have all these theorems. But really, the only publication that there is for this is the slides right here, which I assume will be put on on the website.
They will be available. It's really interesting to know that this is an exclusive theorem from Mathematical Summer in Paris.
This is the publication. and then, you know, yeah, what else can we do? Well, you see, all the Platonic solids have already been classified, and if you know when Plato lived, you can. That means they were already classified a really long time ago. And so here's the list. Yeah, the cube, you know, like ordinary buildings are built with those kind of angles, right? You know, homes, buildings, office buildings, walls, floors, this is all 90-degree angles. So we've seen plenty of this. This is the same symmetry. These two are the same symmetry. And like I said, this here only really can lead to only one reasonable construction toy. And this one, that's a subgroup of that. So whatever it is you could do with this construction toy, you can also do with this one. So really, apart from ordinary 90-degree construction and zometool, that's really it. Okay, so if you wanted to do something else, you'd have to go to 4 dimensions, you know, or higher. Right. Yeah. So what you would do is, but the drawback then is that you can't hold these things in your hand, right? But you could go to the Atlas of Finite Groups, and
it's hard to hold them in your mind.
So look at some really cool groups that have some really cool representations, you know, in dimension 4, and then you could make a 4-dimensional version of Zome, which has like totally awesome connections and all that. But the problem is it's all on the computer, because here, yeah, I just really like the fact that you can prove theorems just by sticking threads in these Zome walls. I just think that's awesome. That's of course never going to happen in dimension 4, and in dimension 3, yeah, okay, what else is there? Yeah, you know, it's not like Plato somehow overlooked the Platonic solid. There's some really nice proofs that those classifications are complete. So that those were known.
Yes. There's only 5
years ago, and there's nothing I can add to that unless you have to go to higher dimension. Yeah, I'm not going to do that.
Yes, this is harder to hold in your hand. Well, thank you very much again for this very nice lecture, Mark. We will have to stop now. I remind everyone in the audience that the Mathematical Summer in Paris resumes tomorrow at 11 a.m. Paris time for a lecture of Jacques-Olivier Moussafir. So see you all tomorrow, and thank you again, Mark, for this very nice lecture.